Hello and welcome to the session. I am Dr. Akshay Kumar from School of Computer Science, IGNOU, and I'll be discussing with you about minimum cost spanning tree, but this time we will be discussing about Prim's algorithm. As discussed in the previous session, that minimum cost spanning tree are basically part of graphs, topic of graphs, where we try to find a tree from within a graph, a subgraph of a graph, which has the minimum cost. Obviously, it will be requiring some representation of the graph. As was the case in the Kruskal's algorithm, Prim's algorithm also uses adjacency matrix, representation of graph. And once again, what you can visualize is that suppose we have a graph, okay, which has, let's say, 8 nodes and 9 edges, or 7 nodes. These are just 7 nodes and around 9 or 10 edges. Then how we can represent, okay? And what you can observe, that all the diagonal elements are zeros and the graph is symmetric in nature. Right? Why symmetric in nature? Because these are, the edges are undirected edges, right? So A to B, A to C also means an edge C to A, because it is undirected, or you can say they are bidirectional, both the direction. Okay, therefore, if you are representing A to C and with the weight of 1, so is the case you will be representing C to A as 1. That is why this particular graph is going to be symmetric in nature. And you can observe that this graph is really symmetric, okay? And symmetric to across the diagonal. And as informed in the previous case, infinite is primarily when there is no direct edge from A to that particular node. For example, A to D, there is no particular direct edge. Therefore, we have put an infinite in this particular case. Now, what this infinite can be? Okay, many times people may ask, what is this infinite value? Well, any large value which you believe is much more than your weights, whatever the highest weight which you have in the graph. All right. So, while actually implementing this particular solution, okay, you might use a very large number as infinite, okay, otherwise not a number is not the solution for this particular situation, okay. And minimum cost spanning tree, once again, if we can look at minimum cost spanning tree, so how many edges are there? So if there are 7 nodes, there are going to be 6 edges, okay. So you have total of 6 edges when you have 7 nodes, all right. So that is a typical property when you are looking at minimum cost spanning tree. So within the spanning tree, a tree has graph connecting all the vertices. It has to connect all these 7 vertices should be connected in the minimum cost spanning tree. It's a tree, right? And minimum spanning tree is basically spanning tree consisting of those edges, so that the overall weight of this particular tree is the minimum. This we have stated in the previous session also, just repeating for this particular session also. Then the properties, once again, properties are that it has V minus 1 edges, MST does not have a cycle, okay. Trees do not have cycles, so is minimum cost spanning tree, okay. MST may not be unique for a graph, they may be multiple, but we are finding one of the solutions over here. And a very important point about the Prim's algorithm, that is, selected edges in Prim's algorithm always form a single tree. In Kruskal's algorithm, if you remember, what we started with A to C, and then we selected A to B, these two edges we selected. After that, we selected this particular edge, right? In Kruskal's algorithm, right? So, this is one tree, this was one tree, and this was another tree. However, the algorithm was such that towards the end, all those disjoint trees were combined into one single minimum cost spanning tree. However, Prim's algorithm always start with this particular thing, that it always forms a single tree. So, it is not going to, maybe it is not going to select edge D to F after selecting A to C. So, how does it work? How does this particular algorithm works is the topic of our interest as far as this session is concerned. So, what is the algorithm as far as Prim's algorithm is concerned? Well, once again it requires at least three basic things, which is set of vertices, which happens to be V, set of edges, which happens to be E, and set of weights, which is basically the adjacency matrix which is going to be fed into the system. Alright, so these were also required in the Kruskal's algorithms also. However, in Prim's algorithm, we always have to represent or always need to give a starting or the root node. Alright, so that is why it is being called R, the root node. Okay. Now, how does the initialization takes place in Prim's algorithm? For each vertex U, which is a member of V, U dot key value is made infinite. So, we will be initializing with key values to be very high. Okay. So, this key value basically will be representing the weight in a particular way. Okay. Then U dot parent. Okay. So, we are basically for this basically, if you see, for each vertex you are doing it, right. So, as many vertices or as many key values you have specified. Then U dot parent is specified a null value. That means we are also keeping another node or another array which is keeping track of all the parent nodes of this particular node. Okay. So, this is basically initialized to be null because till now no parent has been specified, like this particular node belongs to this, the root is this, or that kind of a thing has not yet started, right. And the final thing is that when we are starting, we have already given one R root node. So, we say that the key value, since it is the root node, obviously the overall or the weight of this particular node is going to be 0. So, that key value in this particular case has been specified to be 0. Alright. So, this is what is the basic initialization step as far as Prim's algorithm is concerned. And then we select a not selected vertices kind of a set, which basically consists of all the vertices. Alright. So, this is slightly different from what we utilized in Kruskal's algorithm, because over there the number of edges are going to control the looping construct. In this particular case, the number of vertices, like all the vertices has been selected or not, that is what determines the looping construct. However, it is going to be the same, because ultimately the number of edges you select for this minimum cost spanning tree is V minus 1. Alright. So, there is almost no difference as far as order is concerned in that. Okay. So, while this, that is the not selected NSV, not selected vertices is not null. So, we will repeat this particular step. we will extract the node with minimum key value in this NSV, okay, not selected vertices, okay, and it will be added, it will be removed from NSV, from this particular set, okay. And then for each vertex V, which is adjacent to U, so now we are referring to vertex U, so we will find all the adjacent vertices to node V, that is node U, okay. So, and let's call it as V, okay. If V is a part of NSV, okay, and W, U, comma V, that is W, weight of this particular edge, U to V, is less than V dot key value, what we will do? We will add it, okay, we will change the key value to weight of that particular weight edge, and we will change the parent of this particular node V to U. All right. Now, this looks very, very complicated, but this is very simple if we understand this particular logic with the help of an example. Let me repeat and then go to example. So, what we are doing? We are trying to find, okay, all the adjacent. So, we are picking up the node with the least, what we say least value, or which has the least key value, all right. And that particular node, then we are trying to see all the adjacent vertices of that particular node. And then the weights will be modified into the key value. So, key value will get the weight of the edge, right. So, that key value will be put into the weight of the edge, and the smallest weight then will be selected next. So, that is how key value will be containing the weight of edges, all right, and that will be used to select the next edge. However, the process is slightly different here because we are just considering the adjacent edges, all right. So, all the edges which are far off, okay, they will not be considered till the time they are adjacent to the set of a set where we have already located the, we are able to find the minimum cost spanning tree, that subgraph of that particular tree. What do I mean? Let's look into this example. Once again, the same example we have selected, what we have selected in the last session where we discussed about the Kruskal's algorithm, all right. And we will be dealing with this particular algorithm over here in this particular way. Okay, so how do we initialize? So, for every vertex U, which is part of vertex V, so that is A, B, C, D, all these are the vertices till G, what we have initialized? U dot key values to be infinite. So, if we see, since we have used V in this particular case, so U means V in this particular case. So, U values has been initialized, all the values has been initialized to infinite, but it is looking, this is 0. Why? We will come to that. So, U dot parent have been made as null. So, all these values has been made null, all right. However, the root node, okay. So, in this particular case, we are assuming our root node to be this particular node, that is node A. So, for A, since A has been selected as the root node, therefore, the root node key value is 0 and this is the root. That is why it has been stated that this becomes the root and the value has been initialized to be, the key value has been initialized to be 0. So, it is the minimum, right. So, in the first iteration, obviously it is going to be selected and NSV is given all the nodes. So, NSV basically consists of the set A till G, A, B, C, D and all that, those things will be there. So, this is the way we are going to get this information. Why we have, we have just used these nodes so that we know how these arrays will be manipulated, the parent and the key value, because they are now going to be utilized for selecting the next edge in a sense, okay, but something which has the minimum value. Now you can see this is far off, I said far off. So what you will see, nodes which are closer to it first will get selected, and this edge is going to be utilized somewhere later. So we'll see how it happens. Okay. So this is my first iteration, all right. So in the first iteration, since we have to start, our start node was A, okay. So when we start with A, the value of root is there, value is 0, that's why it has been selected and it has been made permanent. So A has been selected. Now what we need to do, okay, so we extracted A, node A from it, all right. Now NSV contains, A is removed from this particular graph now, in the sense that it has not been removed from the graph, but from the set NSV, which consisted of A, B, C, D till G, right. So A will be removed from this particular set, and for each vertex V adjacent to U. Now let us look into which are the nodes which are adjacent to A, that is how we will check. You can check it in very easily in the adjacency matrix. So A to B and A to C, right? These are the only two edges you can find. Rest all edges will not be there. So these two, that is A to B and A to C, are the only edges, right? Okay. Therefore, for node B, okay, what we are doing here, if V is a member of NSW, so let's consider A to B first. So B is B a member of NSV? Yes, because B, C, D, all these are the member of NSV so far. So B is a member of not selected vertices, okay, and W, U, comma V is less than key value. It had a value of infinite, right, and this value is just 2, A to B is just 2, right. That is what W, U, V. U is A, V is B in this particular case. So it becomes U, A, B, which is less than V dot key value. Yes, V dot key value was infinite. All right. Then what you do? V dot parent is made U. What is U? A, right. So it has been made A, and this particular value, that is V dot key value, has been made as the weight of UV. Weight of UV happens to be 2. So it has been replaced by 2. All right. Let's do it for C. Okay. Now for C, C is also adjacent to A. All right. C is adjacent to A. Is C part of NS not selected group? Yes, vertices. So C is also part of not selected vertices. All right. So C is there. What we find in C now? Okay. So C is there. So that means this condition. And is this weight less? Yes, the weight is the weight of key value was infinite, and the weight of A to C is just 1. Now it is not A to B anymore. It is now we are referring to C, A to C. Okay. So now the parent of C is going to be A. Okay. We started with A. So the parent of C is going to be A, just like the parent of B was also A, and the weight gets changed to 1. All right. So this is how the algorithm is working. Have we come to end of it? No, NSV is not null so far. So we have removed NSV, okay. We have just removed A so far. We have not removed anything B or C. We have just played with the value of B and C, but we have not, only A has been removed from this NSV. So NSV consists of B, C, D, E, F and G. All those nodes are there in the NSV. All right. So now NSV now contains B, C, D, E, F and G, right? Okay. Now which one we are going to extract? Min node. okay, from NSV. Okay, so min node we are going to extract from this particular case. Which is the min node out of the two? This has a value 1, this has a value 2. So, this is what? C is going to be selected next. Alright, and you can see here, this becomes, both these become permanent. Okay, so C will be removed now. So, C will be removed. So, we get NSV as B, D, E, F and G only. Alright, so C has been removed here. Now, once again we are going to check the vertices adjacent to C. Now, adjacent to C, A is already there, so nothing is to be done about A, but C to F, C to D, right? So, D and F are adjacent to C. So, first we will do for CD and then we will do it for CF. For node D and for node F. For node D and for node F, this weight is 6 and 7 7 or 6 you can say respectively. For D, it is 7. So, it satisfies this particular condition. Alright. So, now please note, the parent of D and F will be C. Okay, because the node which we have removed. So, U is in this particular case is C, right? So, the node C is parent of D and F, and the changed weight from infinite, because C to D has a weight of 7. So, this weight is 7, and C to F, okay, this particular node, C to F has a weight of 6. So, this becomes 6. So, you can see that the nodes and the values has been changed accordingly. So, now we have these two nodes. So, this is our subtree. Okay, this is our subtree which is representing the MST. However, the operation is not yet over. Complete algorithm run is not over, but this is the temporary subtree. Okay, let's move to the next step then. Okay, so now we are left with, our selection was among B, D and F. So, we had these three. So, B which is adjacent, B is already there, right. So, since our subtree is basically this one only, right. So, adjacent to AC technically speaking, this is our subtree. So, adjacent are B, adjacent are D and F. So, B, D and F. Which has the minimum weight? 2. So, we will select this particular and it will be made permanent. So, you can see that this has already been made permanent. Alright. Okay. Now, the weights will be adjusted. Alright. How the weights will be adjusted? Now, here is a very interesting case. Okay. When you have made B as the part, alright. So, B has been made part. So, what are the adjacent nodes to B? D and E. Alright. So, they need to be added. Alright. As far as E is concerned, the weight is 3. Right. So, weight has from infinite, it has been converted to 3. But when we look at D, the earlier weight of D was 7. Alright, which had come from C to D node. Alright, that was the weight from C to D. However, the node, that is the H, B to D, has a weight of 4 only, which is less than the key value. Alright, so less than the key value. What was the key value at this point of time? 7. What is the V dot key value? Is 7, and what is the weight? 4. So, it is less, 4 is less than this. That means, parent of D is going to change from C to B. So, parent of, now we are referring to B as the parent, U. So, this particular parent of this node will become B only. All right. So we have removed B and converted it into B, C we have removed and it is now B, and weight is also changed. All right. Same is the case here for as far as E is concerned. It is very easy, from infinite to 3, and F there is no change, already C was its parent. However, over here what you see, now the parent is B for D. All right. So let's move to the next iteration. So let's look into now what are the choices available to us. These 3 were already made permanent. So the choices available to us are this, this and this. What is the minimum? E to B, right? So this node B to E is the choice available to us. All right. It is selected. So you can see this has been made blue. So it has been selected. Now what are the adjacent node to E? Just D, and it has a weight of 5, and already the node for D is 4. That means this condition is false. All right, because the V dot key value is 4, which is less than, right, which is less than the weight, which is 5. So this condition is false. Therefore, we are not going to execute this particular operation, okay, for E to D, this particular edge, because it has a more weight. All right. So because of that, it's okay. Nothing else is to be done as far as this step is concerned. And why we don't need to do? Because the weight of edge E to D is 5, and B to D node, which is already a parent of D, has a weight of 4 only, right? So this condition is false. Both the condition has to be true in order to execute this particular part. All right. So this is the next state which we get. Okay. Okay. Then from here we move to the next situation. So now this was frozen, this was frozen, this was frozen, and this was frozen. Now the minimum of these two was 4. All right. So this 4 has been selected now. All right. So this 4 has been selected. Now D has an adjacent of G as well as F. Now when we look at F, what is the weight? 9, and already there is a weight 6. So this condition is false. No change is needed. This is correct. All right. However, G to F, this particular situation, okay, D to F, G, this adjacency has to be taken into consideration. Okay. So this infinite will be reduced to 2. Why? Because the weight of this particular node is just 2. So this statement, and the root of G is going to be D. So that is what it has been. All right. So you see we have got. So we have got these frozen so far. So we have please note, we are making the tree, and this tree is continuous in the sense that there is no subtrees created otherwise, which was being created in the Kruskal's algorithm. So that is something which you need to note. We are just creating a node or a minimum cost spanning tree, okay, which is one spanning tree only. Okay, there are no disjoint trees which are clubbed into one towards the end. All right. Now is our final choice. So we got to select one of the two from these two. Which one is to be selected? Obviously with the low weight. That is how this will be added. Okay. So now this is my minimum cost spanning tree so far. All right. This has been added. Now G to F, that is adjoining. So will it make any change? No, because the weight is 8 for this particular edge, and already we have found a node which is, or a parent which has a from which it has a lesser node edge, which is 6. Okay, so we'll maintain it, no changes needed here. And finally, this also will be made. This is the last step in this particular case. So CF will be added to this particular tree. Now, how my tree looks like? What is my root? A. All right. From root, what is my next edges? There are two edges from A, B and C, which is basically pointed by my parent this. Then B has two edges, all right. Then C has just one edge. C is a parent of F only, and D is a parent of one node. So this becomes my minimum cost spanning tree, which comes out of this particular situation. Weight against, in this particular case, once again the weight is, you can just add the weight. It is going to 1 plus this 1, 2, 3 and 4. This will be 10, and 6 plus 2, this will be 8. So total weight is going to be 18. It is same as what we have created for the Kruskal's algorithm. Obviously, both of them are greedy approach. Fortunately for us, this particular graph has only one minimum cost spanning tree, so it gave us the same spanning tree. Otherwise, they might have given us different spanning tree, but their weight would have been the same, overall total weight. Now, what is the complexity of Prim's algorithm? Well, as far as Prim's algorithm is concerned, the initialization steps, what we said that for every node, those initialization steps are to be executed, right? And the while loop executes until all nodes are traversed. So it is traversed V times, okay? A node extraction step, when we extract a node, perform using a heap. So you can implement it with the help of a heap. And when you are implementing a heap, when you extract a node, it is just order log V time, right? So since you are extracting V nodes, okay, V number of nodes, so total time will be needed V log V for extraction. So it will be of the order of V log V, okay. So this is what is the order for node extraction. The number of adjacent nodes, adjacent edges can be maximum be 2E. All right. The for loop will require order E only, right? So that is what, as heap is used overall, it will require order E log V only. That is extraction. Once again, E log V, or this is going to be the order. When we add all the orders together, this happens to have the highest order, right? So the order is E log V, which is same as what was the order or complexity for Kruskal's algorithm. So both the algorithms, different approaches, however having the same complexity in this particular case. So let us summarize what we have done in this particular session. A minimum spanning tree is a tree of minimum weight that connects all the vertices of a graph. Prim's algorithm keep adding edges in a set that always forms a tree. Kruskal was not doing that. It selects a new edge which is not part of MST and adds it to the tree only. Okay, so adjacent to the, from tree only you find the adjacent node. Thus it finds the minimum, right? Finds the minimum adjacent one and selects it. So it is a greedy approach only, okay, or the greedy algorithm. And the time complexity of this algorithm, the Prim's algorithm, is of order E log V, which is same as Kruskal's algorithm. With this, we end this particular session. Thanks for being with us.